This video will discuss how differences in molecular structure between saturated and unsaturated lipids lead to their different phases at room temperature and their different melting points. Both butter and olive oil are types of lipids, but they exist in different phases at room temperature. Lipids that are solid at room temperature are called fats, while lipids that are liquid at room temperature are called oils. How the molecular compositions of these substances determine their melting points and why are the questions that we will explore in this video. Butter is a solid at room temperature, but your body heat will liquefy it if you hold it in your hand. A less messy way to observe this is to gently heat it in a frying pan. We see a phase transition as it melts from a solid phase to a liquid phase. In contrast, olive oil is a liquid at room temperature, and you would need to pop it into the freezer to get it to transition to a solid. Where does this difference come from? Dietary fats like butter and olive oil are mostly mixtures of different triglycerides, molecules like the one shown here. Triglycerides are also called triacylglycerols because they can be broken down into three long-chain carboxylic acids, which are called fatty acids, and a glycerol molecule. Fatty acids with no carbon-carbon double bonds are called saturated, while those with one or more double bonds are monounsaturated or polyunsaturated. The double bonds in naturally occurring unsaturated fatty acids typically have cis stereochemistry. As this graph shows, butter has a high saturated fat content, while the triglycerides in olive oil contain mostly unsaturated fatty acid tails. We will see that the difference in saturation contributes strongly to the difference in their melting points. Phospholipids are structurally related to triglycerides, but with one fatty acid replaced by a polar phosphate containing group, in this case, a phosphocholine. DPPC shown here is an example of a saturated phospholipid. It has a positively charged choline group, a negatively charged phosphate group, the same glycerol backbone as the triglycerides, and two saturated tails. Phospholipids like DPPC are key components of cell membranes because they organize themselves into bilayers. As we see in this cross-sectional illustration of a DPPC bilayer, the polar head group components face towards the water. These are the positively charged choline and negatively charged phosphate groups. This leaves the hydrophobic tails sandwiched inside. Like triglycerides, phospholipid bilayers undergo phase transitions that depend on the saturation level of their fatty acids. It is impossible to see the motions of an individual lipid molecule, but we have a pretty good idea of how lipids moved by using computers to simulate their dynamics. To create these animations, we model a patch of hundreds of lipid molecules in a bilayer surrounded by thousands of water molecules. In the animations, we show just the lipids and highlight one typical lipid to show its behavior. At 323 Kelvin, a temperature well above human body temperature, we see that the tails are bending and extending rapidly. In fact, this movie is in slow motion. Real lipids move a billion times faster. Upon cooling to a temperature of 298 Kelvin, we see that DPPC exhibits its solid or gel phase. The phospholipid tails are lined up and remain straight. The apparent flexibility of the lipid tails at the higher temperature comes from rotations around the carbon-carbon single bonds. This rotation is quantified by dihedral angle, which is defined as being at 180 degrees when the neighboring carbon-carbon bonds are rotated a half turn away from each other. For a saturated alkane chain, this conformation has the lowest energy and so is most stable. Dihedral angles of plus or minus 60 degrees, which can be achieved by rotating the bonds by 120 degrees away from this most stable state, are the next most stable conformations. The higher the temperature, the greater the chance that random thermal motion will twist a chain into one of these less stable conformations, introducing a kink and preventing the chain from packing in a solid structure with its neighbors. DOPC is an unsaturated phospholipid that has a similar tail length to DPPC, the main difference being the presence of a single cis double bond in each tail, which are highlighted in orange in the animations we'll show. Here we have simulated a DOPC bilayer at 323 Kelvin. As these simulations show, this monounsaturated tail phospholipid is fluid at both high temperatures and at room temperature, just like olive oil, which is high in unsaturated fatty acyl triglycerides. Let's consider how the presence of a cis double bond might keep DOPC in the fluid state at low temperatures, where we saw that saturated DPPC molecules packed in ordered rows. We see first of all that the cis geometry leads to a bend in the chain. That could complicate packing into an ordered crystal, but that doesn't explain how floppy the DOPC tails appear to be. Let's consider dihedral angles again. Although the pi bond prevents rotation around the sp2 alkenic carbons, rigidly keeping its dihedral angle close to zero, it actually makes it easier for rotations to occur around the bonds that connect the alkenic carbons to their neighbors, the allylic carbons. In contrast to carbon-carbon bonds in saturated chains, for these alkenic allylic single bonds, the most stable dihedral angle is not 180 degrees, but rotated about 60 degrees clockwise or counterclockwise. This brings the unsaturated carbon chain away from the planar structure we are used to seeing represented on paper. The energy barrier to rotate from one conformation to another is lower than in alkanes as well, leading to more rapid transitions. The presence of two of these extra slippery bonds, one on either side of the rigid double bond, will produce an overall more flexible chain that stays liquid at lower temperatures than a saturated tail. The most stable conformation of a saturated lipid tail is extended, with all CC single bond dihedral angles at 180 degrees. The presence of a cis double bond in unsaturated lipids not only produces a bend in the chain, but promotes out-of-plane rotations at the alkenic allylic CC bonds, decreasing the likelihood of solid-like ordered packing arrangement. We hope that when you are preparing and eating foods with butter or olive oil, you will think of how the flexibility of fatty acid tails and the temperature determine whether they are solid or liquid.